In this video, we're going to talk about the functional and concurrent features in Rust and how they work together to provide fearless concurrency and a simple, usable, and very expressive interface for the programmer. The fundament of all functional programming is functions, and while we have looked at functions in the past, we're now going to look at taking functions as values and closures, which are essentially functions that can be defined in line and close over variables in their scope. So what is a closure? As I mentioned, a closure is a function that closes over or captures its environment. This means it's defined in line with other code, and it can access the bindings that were declared in that code. Typically, functions like this, declared in line, are anonymous, although they can be bound to variables, in which case those variables or bindings become their names, but their types cannot be named. You cannot say this function takes this specific closure. As you can see in the example here, we have a function. It declares a binding a, sets a equal to 10. It then declares a closure, and within that closure, it calls a function that uses the binding that was declared in the outer scope. So we say that that closure closes over that binding a. The syntax is pretty similar to a lot of other languages. A closure is written with two vertical bars surrounding its arguments. If you're familiar with, for example, Python, this syntax replaces the lambda, x, etc. syntax in Python, and of course anyone coming from a functional language will recognize this fairly rapidly. As soon as you create a closure and bind it to something, or not, you've created something that implements one of the FN, pronounced fun, family of traits, meaning it can be called with the open parenthesis, close parenthesis syntax, just like a function, and you can see that we do that here. We create a closure, which takes a single variable and returns the value of that variable plus 1, and we then immediately call that in a println macro and display the result, and it will print out 3, because we've created a function that takes a variable and adds 1 to it and returns that, and we've passed it 2. This is just like saying fun closure 1 takes x colon I32, return x plus 1, except that we've declared it in line. Now, this is effectively the same thing, but we're closing over the binding val. So in this case, closure 2 is a function that takes a variable and adds 10 to it. However, we didn't write 10, we wrote val. That's because it's a closure, it's declared in line, and so it can use the bindings that were declared in its same scope. We can't write the type of a function. It's called an anonymous or unspeakable type. To return it or accept it in a function, we are required to use generics. So you can see the code here is actually impossible to write. There's no value that we can put in for type here that will not cause an error. It is impossible to write down the type of a function like this in Rust. However, it is very possible to write down the generic type of a function. So you can accept or return closures with generics or with dynamic trait objects. So both of these functions return functions, and these return functions are functions that take an I32 and return an I32. So there are 3 FN traits, and it's important to know the distinction between them. An FN, or fun, can run any number of times, only closing over immutable bindings. That is, it's essentially just the same as a regular function. Fun_mute can run any number of times, and it can close over both mutable and immutable bindings. And fun_once can run once, and it's allowed to take ownership of captured bindings. Any fun_once implementer can be spawned into a thread, and if you recall from the diagram on the previous slide, all fun or fun_mute implementers are fun_once implementers as well. So any function can be spawned out into a thread. This is done using standard thread spawn, and it creates full OS threads, not like green threads in Go or coroutines in Lua. Here you can see some sample code that does this. We use standard thread. We spawn a new thread with a closure that takes no arguments and simply prints from a thread. Thread spawn is going to return as a handle. Then in the main thread, we print before a thread, and then we say handle.join. And effectively what this does is it says to the operating system, please go do this work on another thread. And then when we say handle.join, we say, okay, let's wait for that work to be done before proceeding with execution. So this is either going to print before a thread and then from a thread, or from a thread and then before a thread. There's not really any way to know, because it's entirely possible that that thread will be scheduled on our same core before us, or it will be scheduled on another core, and our main thread will be delayed for another piece of code to execute on our core. but it's equally possible that our main thread could execute before the spawn thread does anything. The key idea here is that fun trait separation makes concurrency fearless. Think about this in terms of the context of the fun traits. A fun once can do anything it wants because we know it can only be run once. Whereas, for example, a fun mute can't take ownership of things, so it can never deallocate memory, ensuring that running it multiple times is allowed, assuming the exclusivity and mutability characteristics are preserved. And to extend that idea, a fun, not fun mute or fun once, can run any number of times because it doesn't need exclusive access to anything, and it can't drop memory or deallocate any resources, meaning it is safe to run it as many times as possible. It is idempotent, or functionally pure.